High above the war-torn landscape of occupied Europe, at an altitude of 25,000 feet, a P-38 Lightning hurled itself earthward, locked in a desperate pursuit of a German fighter. The American pilot, a mere speck in the vast, cold sky, pushed his controls forward, the twin-boomed aircraft responding with a surge of acceleration. Then, without warning, the world tilted violently. The Lightning's nose tucked sharply downward, the dive steepening with terrifying speed. The pilot, his muscles straining, hauled back on the control wheel with every ounce of his strength. Nothing happened. The controls were frozen, not by a mechanical failure, but by an unseen, insidious force. Aerodynamically locked, they refused to yield. The aircraft screamed past 400 miles per hour, a metallic projectile plummeting towards the distant ground, and the pilot found himself utterly powerless, unable to move the controls even a fraction of an inch. In those harrowing moments, a precious few pilots miraculously recovered. As their aircraft plunged into denser air at lower altitudes, the very physics of the problem would, for an instant, reverse themselves, granting a fleeting chance to regain control before the Earth rose to meet them. But many never had that chance. Their fighters, unable to withstand the immense stresses, simply disintegrated in mid-air, scattering debris across the sky. Lockheed's engineering team had a technical term for this terrifying phenomenon: compressibility. But the pilots, those who stared into the abyss and sometimes returned, had a far more visceral name for it. They called it the death dive. By late 1943, compressibility had claimed the lives of too many P-38 pilots and left an indelible scar on the veterans of the 8th Air Force. The Lightning's once formidable reputation in the European theater began to fracture. German fighter pilots, swift to identify and exploit this deadly flaw, would deliberately initiate steep dives when engaged by Lightnings, knowing their American adversary. The Lockheed engineering team, under immense pressure, scrambled for a solution. Their initial breakthrough came in the form of a small set of electrically actuated dive flaps, designed to mitigate the effects of compressibility. This innovation, while critical in saving lives, inadvertently led them to an even more profound discovery. It was a revelation about hydraulics, about the sheer forces involved in aircraft control, and about the revolutionary potential of removing human muscle entirely from the equation. This is the story of how the desperate race to fix a fatal flaw in one of the war's most iconic aircraft unexpectedly gave birth to a technological leap that defines every fighter jet in the world today. To truly grasp the monumental challenge faced by Lockheed's engineers, one must first understand the very essence of the P-38 Lightning and the urgent necessity for its success within the United States Army Air Forces. The aircraft's lineage traced back to a 1937 Army Air Corps specification, a demanding call for a high-altitude interceptor capable of an astounding 360 miles per hour at 20,000 feet. The Lockheed design team, spearheaded by the visionary Hall Hibbard and featuring the brilliant engineer Clarence Kelly Johnson, immediately recognized the impossibility of meeting such a requirement with any single engine then in existence. Their audacious solution was a radical departure from conventional design, a distinctive twin-boom configuration housing two powerful Allison V1710 liquid-cooled engines. This innovative layout, born from necessity, was the foundation upon which the future of high-speed flight would be built, a future that nearly ended in an uncontrollable plunge. From the very first glance, it was a declaration, a radical departure from the conventional single-engine fighters of its era. The Lockheed P-38 Lightning emerged as a vision of the future, a purse each housed within its own sleek nacelle, extended rearward into twin tailbooms. Between tine blocks or propellers, the innovation extended to its very propulsion, with counter-rotating propellers meticulously engineered to nullify engine torque, ensuring a stable, powerful thrust that promised unparalleled performance. On January 27, 1939, the XP-38 prototype lifted into the sky, immediately demonstrating a performance profile that bordered on the extraordinary. This was no mere incremental improvement, it was a leap. When the P-38 entered operational service, it shattered expectations, becoming the very first American production fighter capable of sustaining level flight at speeds exceeding 400 miles per hour. This blistering pace offered a decisive edge, a new benchmark for aerial combat. But speed was only one facet of its genius. The twin-engine configuration bestowed upon the Lightning an unmatched operational range, a capability that would prove absolutely critical across the vast, unforgiving expanses of the Pacific theater. Imagine the sheer distances, the endless stretches of ocean separating island strongholds. The P-38 could traverse them, reaching targets far beyond the reach of its contemporaries. This extended reach was a strategic weapon in itself. Its offensive power was equal to complex harmonization challenges. As bullets converged from different angles, the P-38 concentrated its entire arsenal directly in its nose. 4 50-caliber machine guns and a potent 20mm cannon fired from a single, convergent point. This meant every round flew true, eliminating the need for pilots to calculate lead or convergence, delivering a devastating, precise stream of fire that could tear apart enemy aircraft with terrifying efficiency. Furthermore, its raw power allowed it to climb faster than almost any adversary it encountered, transforming vertical maneuvers into a decisive advantage. In the Pacific, the P-38 quickly cemented its legend. It became the dominant American fighter, a symbol of air superiority. Its long-range prowess was immortalized in one of the most audacious and strategically vital missions of the entire war: the interception of Admiral Isoroku Yamamoto. The architect of the attack on Pearl Harbor, Yamamoto was a figure of immense strategic importance. On April 18, 1943, a squadron of P-38s embarked on a perilous journey, flying over 400 miles across open ocean, navigating by dead reckoning to intercept the transport aircraft carrying the admiral. Their mission: to shoot him down. The successful execution of this intricate, long-range strike underscored the P-38's unique capabilities and delivered a profound blow to the Japanese command structure. Yet, as the war raged on, the P-38's narrative diverged sharply between the two primary theaters. In the skies over Europe, its story took a different, far more challenging turn. The reasons for this shift were not inherent flaws in the aircraft's design, but rather the brutal realities of the European air war itself, realities that the Lightning was simply not engineered to withstand. 1943 witnessed the European air campaign escalate to unprecedented altitudes, where conditions were nothing short of extreme. At 30,000 feet, temperatures plunged to an astonishing -50 degrees Celsius. The P-38's Allison engines, with their intricate turbocharger and intercooler systems, were not designed for sustained operation in such an unforgiving environment. Engine oil congealed, thickening into a viscous sludge. The intercoolers, meant to optimize the fuel-air mixture, instead chilled it below critical operating limits. Engines sputtered, power output faltered, and at the very moment combat demanded maximum thrust, pilots were forced to throttle back, their machines struggling against the cold. And then there was the insidious, invisible killer: compressibility. In the Pacific, where engagements typically unfolded at lower altitudes, this phenomenon rarely manifested. But in Europe, where bomber escort missions necessitated prolonged operation above 25,000 feet and combat routinely involved high-speed dives, compressibility became a terrifying, regular killer of pilots. It was a problem that baffled the brightest minds. Neither Lockheed nor the Army Air Forces, nor even the advanced research facilities of NACA possessed a complete solution. To truly grasp why the P-38's controls would seize in a high-speed dive, one must confront a concept that, in 1941, was genuinely new to the vast majority of aeronautical engineers: transonic airflow. The P-38 itself never achieved the speed of sound. That was not the essence of compressibility. What transpired was far more subtle and, in many ways, far more dangerous than merely breaking the sound barrier. When an aircraft hurtles through the air, it does not simply glide. It pushes air out of its path, creating pressure waves. As speed increases, these waves intensify, and at certain points on the aircraft's surface, particularly over the curved wings and control surfaces, the local airflow can accelerate to supersonic speeds, even while the aircraft itself remains subsonic. This creates a terrifying, localized shockwave. The smooth, predictable flow of air over the control surfaces, the very mechanism by which a pilot steers, suddenly breaks down. The air detaches, creating turbulence, and the control surfaces, starved of their aerodynamic grip, effectively freeze. The pilot, moments ago in complete command, finds their stick locked, unresponsive as the aircraft plunges uncontrollably towards the earth. It was a battle against an invisible barrier, a fundamental limit of physics that the P-38, for all its brilliance, was tragically ill-equipped to overcome in the unforgiving skies of Europe. As the aircraft hurtles through the sky, its velocity builds, and the very air itself begins to behave in unpredictable ways. The faster the machine travels, the less time the air has to yield, to flow smoothly around its form. Then, at a critical velocity, a threshold is crossed. For the P-38 Lightning, this moment typically arrived somewhere between Mach 0.65 and Mach 0.75. Here, something fundamental, something terrifying shifted in the physics of flight. The air streaming over the wing's curved upper surface, by design, always accelerating faster than the aircraft itself, suddenly began to locally exceed the speed of sound. This happened even as the P-38 as a whole remained firmly in the subsonic realm. When a parcel of air accelerates past Mach 1, it unleashes a shock wave. This is not a gentle ripple, but a violent, almost instantaneous transition, a brutal boundary where supersonic flow abruptly collapses back into subsonic. On the P-38's wing, this invisible wall of compressed air materialized precisely across the center section, the very heart of its lift generation. The shockwave tore through the delicate pressure distribution across the wing's surface. Lift plummeted, specifically in the critical central area. The aerodynamic center, that theoretical point where all lift forces effectively converge, lurched dramatically rearward. When this aerodynamic center shifts aft relative to the aircraft's center of gravity, the nose inexorably pitches down. In the midst of a dive, this sudden, powerful nose-down pitching moment was catastrophic. It compounded the existing dive angle, forcing the aircraft into an even steeper, faster descent. This acceleration, in turn, intensified the airflow over the wing, which strengthened the shockwave, which then drove the nose down with even greater force. A horrifying, self-reinforcing spiral of destruction. Adding to the pilot's nightmare, the elevator, the crucial control surface designed to pull the nose up, found itself directly immersed in this maelstrom. Positioned just behind the wing, it was blanketed by the shockwave's chaotic turbulence. The elevator lost all authority. Pulling back on the control wheel, a desperate instinct, became utterly futile. There was no clean, undisturbed airflow for the elevator to bite into, no leverage to be found in the violent churning air. From the pilot's perspective, the sequence of events unfolded with terrifying speed. A routine dive, acceleration beyond an unseen, unfelt boundary. The nose violently tucks downward. The controls freeze, unresponsive, inert. Nothing works. The dive steepens, the ground rushes up. Survival hinged on a single desperate hope: that the aircraft might descend into denser air below 15,000 feet. At lower altitudes, the same true airspeed represents a lower Mach number, and the physics of compressibility could, miraculously, reverse. Or it simply wouldn't make it that far. What rendered compressibility so uniquely perilous was its insidious nature. It was utterly invisible, completely counterintuitive. The P-38 would feel perfectly normal, stable, predictable, right up until the precise instant it wasn't. There was no warning vibration, no unusual sound, no instrument needle that twitched to flag the approaching threshold of disaster. A pilot encountering this phenomenon for the first time had no instinct, no training, no sensory cue to prepare for the sudden, absolute loss of control. It was an ambush from within the very air itself. The National Advisory Committee for Aeronautics, NACA, had been aware of this theoretical phenomenon since the late 1930s. But understanding it in the abstract, within the confines of a wind tunnel or a mathematical equation, was a world apart from solving its deadly manifestation in a production aircraft, pushing the boundaries of what was physically possible. The skies, once a realm of predictable forces, had revealed a new, invisible predator, demanding a revolution in understanding and design. The year was 1941. Flight itself was still a nascent science, hurtling toward an invisible wall. Engineers pushed the boundaries, but their tools remained stubbornly analog. Wind tunnel technology, the very bedrock of aerodynamic research, proved woefully inadequate for the speeds now being achieved in the air. It simply could not reliably replicate the chaotic, violent dance of transonic flow. The air itself became a treacherous, unpredictable entity. Between Mach 0.65 and 0.75, the behavior of shock waves defied understanding. They materialized without warning, invisible fists punching holes in the smooth flow, making precise reproduction and measurement an impossible task within the confines of a laboratory. This was a frontier where theory met brutal reality. In a desperate bid for clarity, the National Advisory Committee for Aeronautics, NACA, painstakingly constructed a 1/6 scale model of the P-38 Lightning. This miniature marvel was destined for the massive 16-foot wind tunnel, a colossal effort to peer into the heart of the problem. The tests confirmed the mechanism, revealing the terrifying forces at play. Yet, understanding the problem was not solving it. The knowledge, though vital, offered no immediate path to safety. Meanwhile, high above the battlefields of a world at war, pilots were dying. They were not falling to enemy fire, but to an unseen adversary: compressibility. The P-38, a marvel of speed and power, became a deadly trap when pushed beyond certain limits. Kelly Johnson, the legendary chief engineer at Lockheed, would later recount the personal toll, the gnawing anxiety that led to a broken ulcer. His team was venturing into a speed range previously unknown, a realm where the very air turned hostile. The struggle was not just against physics, but against skepticism. Many believed the P-38's distinctive twin-boom design was inherently flawed, an odd-looking airplane destined for trouble. Johnson and his engineers fought to convince the world that this was not a design defect, but a fundamental physical phenomenon, a barrier that threatened to halt the advance of aviation itself. Lockheed's engineering team toiled relentlessly, chasing solutions down every conceivable avenue. They experimented with servo tabs, small auxiliary surfaces designed to aid control. They thickened tail structures, hoping to stiffen them against the buffeting forces. They meticulously reshaped wing profiles, searching for a design that could tame the unruly airflow. Each attempt, a testament to their ingenuity and desperation, ultimately proved insufficient. None of these modifications truly addressed the root cause of the terrifying nose-down pitching moment that seized the aircraft in a high-speed dive. The core problem remained, elusive and deadly. The breakthrough, when it finally arrived, was a testament to persistent inquiry and a radical shift in perspective. The solution that ultimately worked, and which would later inform the groundbreaking discovery of the aileron boost system, was elegantly simple. This simplicity was only apparent once the engineers had stripped away the layers of misunderstanding and grasped precisely what needed to change. By February of 1943, after countless hours of design, fabrication, and perilous test flights, Lockheed's courageous test pilots had unequivocally proven a workable solution to the dreaded compressibility dive. It was a deceptively small modification, a set of electrically actuated flaps. These flaps were mounted not on the wing's trailing edge, but outboard of the engine nacelles, on the underside of the main wing. These dive flaps, each measuring a mere 4 feet 10 inches in span, were engineered for rapid deployment. In approximately 1.5 seconds, they could deflect downward by 35 degrees. Their genius lay not in their ability to simply slow the aircraft as a conventional speed brake would. Their effect was far more nuanced, more precisely targeted at the heart of the aerodynamic problem. By deploying downward at that specific location on the wing, just outboard of the engine nacelles, they created a localized disturbance. This disturbance subtly but powerfully influenced the pressure distribution across the entire wing surface. Crucially, this shift in pressure effectively moved the aircraft's aerodynamic center forward. The violent nose-down pitching moment that compressibility induced was directly counteracted. With the aerodynamic center now restored to a more stable position, the pilot regained full elevator authority. The aircraft could pull out of its terrifying dive. Control was returned. Lives could be saved. The concept, proven in the crucible of flight tests in February 1943, demanded immediate implementation. By late 1943, Lockheed had begun mass production, assembling several hundred field modification kits. These essential packages were destined for P-38s already serving in the European, North African, and Pacific theaters, a race against time and the invisible enemy of high-speed flight. The kits, each a promise of survival, needed to reach their aircraft. This critical logistical challenge, fraught with the perils of wartime transport, became a tragic intersection of ingenuity and the brutal realities of combat. In March of 1944, high over the unforgiving expanse of the Atlantic, an RAF fighter pilot on patrol spotted a distant aircraft. His training, honed by countless hours of vigilance, identified it as a German Focke-Wulf FW-200 Condor, a formidable 4-engine aircraft used by the Luftwaffe for maritime patrol and reconnaissance. Without hesitation, he engaged. The engagement was swift, decisive. The large aircraft, caught unawares, plummeted into the unforgiving waves. Only later was the devastating truth revealed. The aircraft was not an enemy Condor. It was an American Douglas C-54 Skymaster transport, a vital artery in the Allied supply chain. A tragic case of mistaken identity in the fog of war. Aboard that transport, lost to the depths, were 200 of those precious dive flap kits. 200 chances for P-38 pilots to survive the unseen forces of the air, gone in an instant. The very solution designed to save lives became a casualty of the conflict it sought to mitigate, a stark reminder that even the most brilliant engineering could not escape the unpredictable, devastating calculus of war. The war machine churned, but not without its agonizing delays. Urgent modification kits, vital for the P-38 Lightnings battling across the European theater, vanished. Lost somewhere in the vast, chaotic arteries of wartime logistics, these critical components meant pilots on the front lines, facing the relentless Luftwaffe, waited. Each passing day without the necessary upgrades was a day of heightened vulnerability, a silent burden on those who flew. Eventually, the solution shifted from field modifications to factory integration. 210 P-38J aircraft, specifically from the J-25 production block, rolled off the assembly line bearing the crucial die flaps already installed. Yet, these machines carried another innovation, a less publicized but equally transformative system: hydraulically boosted ailerons. And it is here, in the subtle mechanics of control, that an entirely new dimension of the P-38's legend unfolds. The P-38's aileron challenge was distinct from the infamous compressibility problem, though the two were often intertwined in the minds of the pilots who wrestled with both. The Lightning was a marvel of design, its distinctive twin booms and 52-foot wingspan granting it exceptional stability, a rock-solid platform for its formidable armament. But this very stability, forged by its expansive wings, created an unforeseen adversary: heavy, sluggish ailerons at high speeds. An aileron, a seemingly simple control surface positioned on the outer trailing edge of each wing, dictates the aircraft's roll. To initiate a turn, to bank right or left, the pilot manipulates the control wheel. A right turn sends the right aileron upward, diminishing lift on that wing, while simultaneously deflecting the left aileron downward, amplifying lift on the opposing wing. The differential in lift then forces the aircraft to roll, executing the desired maneuver. At lower, more sedate speeds, the forces required to command the P-38's ailerons were perfectly manageable. The pilot's input translated directly into responsive movement. But as the Lightning pushed its powerful engines to their limits, as airspeed climbed, the aerodynamic pressure exerted against those deflected aileron surfaces escalated dramatically. This force, in a cruel twist of physics, did not merely increase proportionally with speed. It intensified with the square of the airspeed. What felt light at 200 miles per hour became a leaden struggle at 400. In the maelstrom of high-speed combat, where fractions of a second meant the difference between life and death, deflecting the P-38's ailerons demanded an almost superhuman physical effort. Pilots, their arms already burning from sustained G-forces, found the controls growing increasingly resistant, heavy, and unresponsive. The precious seconds lost fighting the stick meant lost opportunities, lost targets, and a crippling reduction in the aircraft's roll rate, a critical metric in a dogfight. The once nimble Ls most needed. The engineers, ever vigilant, turned to a proven technology, a solution long employed in the brute force world of heavy ground machinery and the complex control systems of larger aircraft: hydraulic power assistance. Their concept was elegant in its simplicity. Instead of the pilot's raw physical strength directly manipulating the aileron through a labyrinth of cables and pulleys, a hydraulic actuator was seamlessly integrated into the control circuit. The pilot's input now served a different purpose. It no longer fought the wind directly. Instead, it moved a small valve. This valve, in turn, precisely directed pressurized hydraulic fluid into a cylinder. The cylinder, imbued with the immense power of the hydraulic system, then moved the aileron with an authority far beyond the capabilities of human arms. The battle against aerodynamic loads was no longer the pilots alone. The transformation was immediate, profound, and utterly liberating. Where pilots had once grappled with mounting aerodynamic resistance that grew exponentially with speed, the hydraulic system now absorbed those formidable loads entirely. The control force experienced by the pilot became remarkably consistent, almost constant, irrespective of the aircraft's speed. Whether cruising at 200 miles per hour or screaming through the sky at 400, the control wheel demanded precisely the same manageable effort to move. The pilot's physical strength was no longer the limiting factor in the P-38's roll performance. The aircraft, once a beast to be tamed, became an extension of the pilot's will, ready to dance in the skies with newfound grace and lethal precision. The P-38 J-25 Lightning, a marvel of wartime engineering, possessed a secret weapon hidden within its sleek, twin-boomed form: hydraulically boosted ailerons. This groundbreaking innovation bestowed upon the aircraft a roll rate at high speeds that not only surpassed the formidable P-51 Mustang, but also eclipsed the legendary Focke-Wulf 190, a German fighter celebrated for its exceptional agility above 350 miles per hour. Lockheed's visionary engineers had not merely refined existing technology, they had fundamentally redefined the very act of flight control. What they had created was universally recognized as the world's inaugural application of powered flight controls to a production fighter aircraft. This was a paradigm shift, a silent revolution in the cockpit. The pilot, once directly linked by cables and pulleys to the control surfaces, now commanded a machine that did the heavy lifting. The human hand issued instructions, and the hydraulic system translated them into immediate, powerful action, amplifying every subtle command. This foundational principle, where the pilot's effort is augmented by mechanical power, became the bedrock of every single fighter aircraft built since 1944, a testament to the P-38's pioneering spirit. Yet, at the very heart of the P-38's narrative lies a profound and bitter irony. By the time the J-25 block, fully equipped with its crucial dive flaps and that revolutionary hydraulic aileron boost, finally reached operational squadrons, a fateful decision had already been cast. The Lightning, for all its advanced capabilities, was destined for replacement in the brutal European theater. Its successor would be the P-51 Mustang. The Mustang, in its definitive D model, powered by the magnificent Rolls-Royce Merlin engine, had arrived in Europe in late 1943. Its impact was immediate and undeniable. It soared into the frigid, high-altitude skies where the P-38 had often faltered, demonstrating a superior performance profile perfectly suited to the conditions. The Mustang was smaller, a more agile silhouette against the vast European sky. It was significantly more economical, costing roughly half that of a P-38 to produce, and proved far easier to maintain in the field. Crucially, it was immune to the debilitating compressibility problems that had plagued the Lightning, damaging its reputation and limiting its effectiveness over the battlefields of Germany. In a poignant attempt to salvage the P-38's standing, Lockheed test pilot Tony LeVere embarked on a personal morale tour of Lightning bases across England in March of 1944. Flying a fully modified J-25 model he affectionately named Snafu Perman, LeVere performed breathtaking maneuvers that, according to the prevailing wisdom of the 8th Air Force, were considered suicidal for any Lightning pilot. He aimed to visually demonstrate the sheer, untapped potential of the improved aircraft, to reignite the spark of confidence in its pilots. The airmen watched, transfixed, their faces reflecting a mixture of awe and renewed hope. They were undeniably impressed, but the wheels of institutional decision-making had already turned, grinding forward with an unstoppable momentum. By mid-1944, the skies above Europe began to tell a new story. Most 8th Air Force P-38 groups had completed their transition to Mustangs, leaving the twin-tailed fighter to a more specialized role. Only the 474th Fighter Group, operating within the 9th Air Force, continued to fly the Lightning until the war's conclusion in Europe. Their missions were predominantly low-altitude ground attacks, where the once critical issue of compressibility became largely irrelevant, allowing the P-38 to excel in a different, yet equally vital capacity. Across the globe, in the sprawling, island-dotted expanse of the Pacific, the P-38's narrative unfolded in stark contrast. There, the Lightning reigned supreme, remaining the dominant American fighter throughout the entirety of the Pacific campaign. The environmental conditions, the altitudes and temperatures of Pacific combat meant the dreaded compressibility problem was far less acute, rarely hindering its performance. More importantly, the P-38's extraordinary range, its devastating firepower, and the inherent reliability of its twin engines over the vast, unforgiving ocean distances rendered it utterly irreplaceable. For pilots facing thousands of miles of open water, the second engine was not merely a backup, it was a lifeline, a promise of return. This unique synergy between aircraft and theater forged legends. Richard Bong, who would ascend to become America's highest-scoring ace of all time with 40 confirmed aerial victories, achieved every single one of them exclusively in the cockpit of a P-38. Close behind him, Thomas Maguire, second only to Bong with 38 victories, also flew the Lightning throughout his illustrious career. Their unparalleled success was not merely a testament to their skill, but to the P-38's perfect adaptation to the specific crucible of Pacific warfare. The P-38 Lightning, a machine born of audacious vision and relentless innovation, found itself caught in the cross-currents of war. Too late for one theater, yet perfectly suited for another. Its legacy is a complex tapestry of triumph and missed opportunity, a powerful reminder that even the most revolutionary technology is ultimately judged by the unforgiving demands of its time and place. It was, in its essence, a fighter ahead of its time, its true brilliance only fully realized when circumstance aligned with its inherent strengths. By the early 1940s, the skies over Europe had become a brutal crucible, a proving ground where aircraft were pushed to their absolute limits. Here, the Lockheed P-38 Lightning, a marvel of twin-boom design, found itself struggling. Its reputation, once gleaming, began to tarnish. The hydraulic aileron boost system, a desperate measure, arrived too late to fully salvage the Lightning's standing in that unforgiving theater. Yet, its arrival was not in vain. It demonstrated something profound, something every aircraft manufacturer across the globe watched with bated breath. Powered flight controls were not merely a possibility, but a dramatically superior necessity for the next generation of high-performance aircraft. The hydraulically boosted aileron system on the P-38J-25 was not a happy accident. It was the deliberate, calculated outcome of genius. Hal Hibbert and Kelly Johnson's engineering team had meticulously identified the crippling issue of heavy ailerons at high speeds, a phenomenon linked to the then mysterious forces of compressibility. They studied the nascent technologies available, then applied hydraulic power with precision, a bold stroke to conquer an intractable problem. What truly astonished them, what the engineers could not possibly have anticipated, was the sheer scale of the revolution they had unwittingly ignited. The principle of powered flight controls, first demonstrated so clearly on the P-38J-25 in 1944, transcended its immediate purpose. Within a mere decade, it became the universal standard for military aircraft worldwide. The post-war era ushered in the age of the jet fighter. These machines moved at speeds that dwarfed anything propeller-driven, generating aerodynamic loads on control surfaces so immense they would have been physically impossible for any human pilot to overcome directly. The hydraulic boost system, a direct descendant of that original Lockheed application to the P-38's ailerons, was not just an enhancement. It was the very enabler of jet fighter control. Without it, the dazzling agility and blistering speeds of these new titans of the sky would have remained an unreachable dream. This fundamental principle, refined, extended, and digitized over decades, ultimately evolved into what we now know as fly-by-wire. Today, this sophisticated architecture forms the nervous system of every modern commercial airliner and military aircraft in operation. In a fly-by-wire system, the raw mechanical connections of yesteryear are gone. There is no direct linkage, no physical cable or rod stretching from the pilot's controls to the aircraft's control surfaces. The pilot's command begins as an input to a stick or a wheel, a subtle movement, a precise intention. This input is instantly translated into an electronic signal, received and processed by an onboard computer. The computer, with lightning speed and flawless precision, then sends its own commands, not to cables, but to hydraulic actuators. These actuators, the silent muscles of the aircraft, respond by moving the control surfaces, guiding the massive machine through the air with effortless grace. Consider the Airbus A380, a behemoth of the skies, or the F-22 Raptor, a stealth fighter of unparalleled capability. Even the Boeing 787 Dreamliner, a symbol of modern air travel. Every single one of these titans traces a direct, unbroken lineage back to a single pivotal decision made by Lockheed engineers in 1943. The choice to route hydraulic fluid through the aileron circuit of a struggling twin-boom fighter, desperate to hold its own in the brutal European air war. The P-38, in the end, lost its preeminent place in that distant conflict. But the engineering principle it so powerfully demonstrated, almost as an afterthought, quietly, inexorably, took over the entire world of aviation. The P-38 story is, at its heart, a profound narrative about the human spirit of ingenuity. It reveals what happens when engineers are forced to confront a problem at the absolute edge of human understanding, pushing against the very limits of known physics, only to discover something far more important, something far more universally applicable than the specific solution they were initially seeking. Compressibility in 1941 was a terrifying enigma. Engineers knew it existed. They understood its devastating effects, how air, at certain speeds, could seemingly transform into an impenetrable, invisible wall, rendering control surfaces useless and tearing aircraft apart. Yet, they could not fully explain it, model its behavior with precision, or reliably test its boundaries. It was a frontier of the unknown, a silent, deadly adversary. And in confronting it, in building a simple hydraulic solution for a single aircraft, they inadvertently laid the cornerstone for every aircraft that would ever fly beyond the reach of human muscle alone. Above occupied Europe, pilots were dying. Their aircraft, pushed to unprecedented speeds, encountered forces unknown to previous generations. The engineers tasked with solving the P-38's deadly deficiencies found no answers in established textbooks. They were, in essence, writing those textbooks in real time, under the immense pressure of a global conflict. The immediate, terrifying problem of high-speed dives, where control surfaces could lock solid against the air, found its radical solution in the dive flap. This aerodynamic brake allowed pilots to regain command, pulling their lightning fighter effort required to maneuver at speed. The hydraulic aileron boost system emerged as the answer, a revolutionary concept that fundamentally altered the pilot-machine interface. Together, these innovations forged a new paradigm. They offered the first production demonstration that a pilot no longer needed to physically overpower the immense aerodynamic forces of a high-speed aircraft. The machine, with its newfound hydraulic muscle, could absorb the punishing loads. The human, freed from brute strength, could provide pure intention. This was not merely an improvement, it was a profound redefinition of flight control. Every time a commercial airline passenger settles into their seat, trusting their safety to a pilot's hands on a control column, they are unknowingly relying on this principle. Those hands, moving sensors rather than directly pulling cables, embody a silent trust. It is a trust in a concept that Hall, Hibbard, and Kelly Johnson's engineering team forged in the aluminum and hydraulic world of a wartime fighter. They proved that human will, amplified by technology, could conquer the skies. The P-38 itself remained a complex machine. It was controversial, temperamental, and expensive. In the very theaters where it was most desperately needed, it was often replaced before its most refined versions could arrive. Yet, it was this very aircraft that taught aviation how to fly faster than human muscle alone could ever manage. This is an engineering legacy that rarely garners prominent chapters in history books, but it manifests undeniably every single time a modern aircraft lifts from the ground, a testament to the quiet brilliance born from the crucible of war.